Okay, and the next tip that I have is before we start moving to the heavy stuff. Yeah, before we start moving to the heavy stuff, it is important to have save files because HYSYS is very prone to crash for no reason, especially when your flow sheet gets more and more complicated. So it is quite important to make sure that you save frequently. But you also reduce your pain by first having multiple save files and save over this milestone. For example, I have defined the stream, I save. I have set up the equipment, I save again in a different file name. Then I have gotten the result, I save again under a different file name. So this will ensure that when something happens, I can recover my work. I don't have to do everything from scratch. You can also save as two different file formats. The first is called HSC, which is HYSYS case. And the second is XML file format. The difference between these two main file formats is that the XML will not remember your result. It will not remember your result. So you have to run the simulation to get the results. Whereas the HSC will remain the old results. So in many cases, you want the old results to be saved. But in some cases, if your simulation cannot converge for some reason, you might want it to reset the results. So you can load this XML file, and then the results will start from 0, and then you recalculate again. And next is also to read from error messages and learn from them. Don't ignore the errors because they usually tell you what is happening. It's just that they don't tell you what you need to do. So you don't have to learn that either from the in-program help or from experience. So let's move on to the third case study we have for today, which is the reactions. So you can go back to this slide, right? We see that there are 4 main types of flow sheet blocks. We have heat transfer, we have pressure changes, we have reactors, and we have separators. So if we have covered the simple ones. I started with the simple ones, the pressure change, where you only need to give it the pressure change, which is the pump here. And you also have a heat transfer block where you need to give it the pressure difference. You also need to give the heat duty, right? So these two are like very simple blocks that anyone can program. The next two are going to be tough because they require a lot of inputs. And we go for the easier one, which is the reactors. So let's look at reactions. So in chemical engineering, certainly we need to have reactions. Otherwise, that's not chemical engineering. This is able to simulate very rigorous reactions, very rigorous reactions. But the issue is that just that you need to have the reaction data, which is quite difficult to get. And in many cases, the heat of reaction needs to be considered. So your substance, whatever that's having a reaction, might get hotter or might get colder, depending on whether the heat of reaction is negative or positive, or you could say that the reaction is exothermic or endothermic. Alright, so Dave has another friend today whose name is Duns. So if you are a bit perceptive, you realize that there's a team naming to Dave's colleagues. Right? So Dave's colleagues Duns today wishes to model a new hydrogen production unit. Because apparently this refinery has a hydrogen demand. There are some customers who buy hydrogen or something. But Duns is not sure which reactor type is the best for this application. So in this so-called hydrogen production unit in the refinery, the two most common reactions we have are steam methane reforming, or SMR. Where you take methane, you react with steam, produce hydrogen and carbon monoxide. This carbon monoxide then goes into what we call the water gas shift, or WGS reaction, where you react with more steam to produce hydrogen and CO2. So the final product should be only hydrogen and CO2. So we are very lucky today that these two examples are very simple examples that HYSYS have the kinetic data in its built-in library. However, I'm going to show you how to input the kinetic data ourselves, because in reality, you are getting kinetic data from a textbook, you are getting it from a journal article, you are getting it from a conference paper, maybe. So, or maybe in your own lab results. So in these cases, HYSYS will not have these kind of reactions and you have to input them yourself. So I'll just show you by doing the first one manually. And for the second one, we will do it, this one we'll do it manually for the steam methane reforming. And second one, we'll just see how we can import the HYSYS reaction. All right. So these two reactions in the hydrogen process, I'll show you the air products hydrogen production unit, where you have natural gas going in. You take out any sulfur you have in natural gas to prevent catalyst poisoning. It goes into the fire heater, and it goes into, so the gas goes into here, it gets heated, and then it goes into these tubes. And there's some catalyst in these tubes where the SMR process happens. So the SMR is a catalytic process. Then the gas goes out, a mixture of hydrogen and CO. It goes into a boiler to reduce the temperature to the suitable for the next reaction. And then it goes into the water gas sheet reactor, where this is where the WGS reaction happens. And then it goes into some cooling and further purification before the hydrogen goes to the customer. So we are going to simulate this and this. So in real life, you will do it in different reactors, but in this case, we will just do it in a simple way, which is we just combine into a single unit. So there are three main types of reactor models in HYSYS. The first type is called equilibrium, which is calculated based on chemical equilibrium. So the equilibrium has to be defined by you, by the user. The second reactor is called the Gibbs reactor, which you don't have to define anything. You just tell HYSYS, these are the components and these are the products. HYSYS will adjust the reactor itself to minimize the Gibbs free energy of the products. So it sounds easy, but later I'll show you why Gibbs reactor is not necessarily the best way. In many cases, it's very, very inaccurate. And the last method is to have a kinetic reactor, which will need us to input the kinetic model or the reactions ourselves. The two most common will be the continuous stir-type reactor for liquid or aqueous applications, and then the plug flow reactor for mostly gas reactions. So this is the one that we are going to use for the plug flow reactor. So I have gotten from the source the rate equation for the SMR process, which is quite complicated. All right. And these are the units. So we'll use this information only for reaction 1. For reaction 2, we'll just use the built-in reaction library. So don't make our own life more difficult than it needs to. All right. So I'll just go back to my HYSYS script.